Okay, got it.
Now we got
All right,
no, right? Is it good?
good enough. We can get started. And
Yeah.
maybe if you just want to tilt the camera down so I could see the room, that's always helpful if there's any questions. I'll try to make this as interactive as possible given the technology available. So I'll stop throughout just to see if we can have a little discussion, and hopefully the audio works well enough. But hi, everyone. Nice to meet you. My name's Ari Spiegel. I'm a senior engineer with BC Hydro, and I'm in the Innovation and Delivery Group, which helps to support our various programs, whether that's energy efficiency, low carbon electrification, demand response, all sorts of incentive programs that we offer. So I've been in the industry for over 10 years now, working previously as a consultant in HVAC, doing a lot of mechanical system retrofits in commercial buildings, as well as a lot of controls work. And then my focus more recently has been on the residential sector in low carbon heat pump technology. So today I want to talk about, sorry, 1 second as I let people into the room. Our agenda for today follows just sort of a heat pump technology overview with a specific focus on cold climate heat pumps. And I'll kind of go over some design considerations, both applicable for sort of general heat pumps, no matter where you're installing them, as well as sort of specifics around northern communities in BC. Talk a little bit about the financials, as well as environmental impact, the use of refrigerants, and greenhouse gas emission reduction. And we'll have questions at the end, but I think we'll stop throughout and see what we can do as we go through some of these concepts. So not sure where everyone is in terms of their understanding of heat pump technologies. So I'll kind of run through very quickly, what is a heat pump and how does it work? And just checking, audio good? I see some thumbs up,
Yeah,
thanks.
it's good.
Excellent.
It's good.
So when we talk about a heat pump, what are we talking about? In the residential space, we're often looking at what's called an air source heat pump. So a heat pump in general is a device that's used to move thermal energy from lower temperature to higher temperature and make it useful. So similar to a refrigerator works, the only difference in terms of heat pumps is that it's a fully reversible system. So in this image, it shows the sort of key components of a heat pump. On the outdoor side, on our air source side, we have a fan and a coil, which is used to absorb that heat or cooling energy. It is driven by a compressor, so that's a electric compressor that moves a refrigerant from one side to the other. And then on the inside, we have that same coil and fan system that's used to deliver heat or cooling to the space. It's a totally reversible system, and sort of those are kind of key pieces that we're looking at. What this looks like in a conventional central heat pump system, your outdoor unit, which you would typically see, contains most of those components. It contains your outdoor coil, your outdoor fan, as well as that compressor, reversing valve, and all the control systems. What we have going inside is just a refrigerant line, which is used to move that heat, and then some device to help move that into the home. So in a central system, you'd have an air handler, which is a fan system with that refrigerant coil. And then it's duct throughout the house, very similar to a furnace-like system. So you'd be supplying, we're going to talk as in just heating mode, you'd be supplying hot air to the space through ductwork throughout your house. You have return air coming back at a colder temperature because it loses some of that heat. And then it goes back through the fan across that refrigerant coil. Meanwhile, the refrigerant's being piped through the outdoor, absorbing heat and delivering it into that furnace air handler system. We also have what's called a ductless system. So a ductless system, again, has that same outdoor system. These are split systems as there's two components connected between refrigerant lines. So on the outdoor side, we have that same component, compressor, outdoor coil, and fan used to absorb that heat. We have refrigerant line going into the building, but then we would have just a single unit fan with a coil delivering heat to one space, so no ductwork. And this is typically what you see in air conditioners. They're called mini splits that maybe just serve single zones. So very sort of systems that we're used to and seen for a long time. So I'm going to refer to these different types of systems and setups because they impact a lot of the design characteristics and operation and some of the challenges when switching from, say, a gas-fired furnace to a heat pump system. Just to run through some terminology, just to be familiar, what I'm going to reference here, a few terms to know. So the first one is our coefficient of performance, our COP. COP is a measure of useful heating, so how much heat output divided by how much energy is provided to the compressor to deliver that heat. So typical ratings of heat pumps would be a COP of 3, which indicates that we're getting 3 units of heat out for every 1 unit of electricity in. So it's can be considered as an efficiency. Another rating system that we use on residential heat pumps is a heating seasonal performance factor. And it's HSPF 2 because they've recently updated the methodology in calculating it. So it's a little bit different than HSPF without a number. So 2 is our current metric that we're using. And it's an indication, not, it's similar to COP, but it's an indication of the total heat output over an entire season. So not at a specific operating point, but throughout a winter. And they'd use sort of specific weather data. They assess what that heat output might look like in BTUs divided by the total electricity in. So in that case, the higher number again indicates you're getting more heat out than you're putting in, so better efficiency. Nominal or rated heating capacity. This is how much heat can be delivered when the outdoor temperature is 47 degrees F or about 8 degrees Celsius. And why we use this nominal rating is, and I'll talk about it in some more detail, is that the amount of heat that can be delivered by an air source heat pump changes with air temperature. So we need to pick a spot to actually rate it so we can get a comparison between specific units. And I think historically, heat pumps were generally used for more mild environments, mild climates, so that rating is done at 8 degrees Celsius. Now we want to see ratings at much colder temperatures because that's what really matters to us is how well can this heat when the outdoor temperature gets quite cold. So they've made some other metrics, and one is a capacity factor. The capacity factor is the percent of heat provided when the outdoor temperature is now 5 degrees F or minus 15. So if we're rated at 8 and you have 100% capacity factor, that means at 8 degrees Celsius, you'll get the same amount of heat as at minus 15 Celsius. But again, most often, these heat pumps drop off significantly as you get to colder temperature and they can't provide as much heat. It's harder for the compressor to move that refrigerant. It's harder to absorb as much heat. So we see capacity factors start to drop. And I'll talk about the cold climate capacity factors in a couple slides. Cutoff temperature refers to the outdoor temperature where the heat pump just can't operate at all. So it's so cold, the oil it starts to chunk up, the compressor can't run, it builds pressure, and it just stops. So that's a cutoff. And that's typically not a rated value. It's more of a performance factor. And then in heat pumps, we have single stage. So this is like your air conditioner. They have a fixed capacity. They provide a certain amount of heating or cooling. And as soon as the room hits set point, they just turn off. And then when it drops, they turn back on and they cycle on and off. Variable speed refers to the ability for a heat pump to actually modulate its capacity so it can match the loads of a home. So as it gets colder and colder and you need more heat, the heat pump can actually ramp up. So it runs more continuously at lower speeds to meet the needs. And these tend to have higher efficiency factors like HSPF2 and COPs because they can very well match the load. So now I just want to take a few minutes and talk about heat pump capacity and heating loads. So this chart really, this graph kind of summarizes everything we're doing when we're looking at heat pumps and design. So starting on this yellowish or brown line is the output of a heat pump. We've got heating capacity in MBH on the y-axis here and outdoor temperature on the x-axis. So say when it's 20 degrees, actually, can you see my mouse pointing to, is there a pointer on this? Let me see, hold on, bear with me 1 second. Let's see what we're talking about. Yeah, so if we're operating at this point, so it's 20 degrees out, Celsius outside, your heat pump can produce a lot of heat. So this kind of indicates it can produce, 60 MBH of heating. As it gets colder and colder, its ability to provide heat is reduced. And we could see, down at minus 15, it's around that, 40 mark. Meanwhile, how does your home respond to changing outdoor conditions? Well, when it's 20 degrees outside, you don't actually need that much heating. So the heating load in the home is very little. But when it gets quite cold, we see that, you follow the line up and at different temperatures, the heating loads increase. So the balance point, which is a really important point for design, is where the heat pump and home are matched. So the output of the heat pump equals the heating load of the home. When it's warmer than that point, it means we have excess capacity on our heat pump, which is good. But when it's colder than that, we can no longer meet the needs of the home, and that needs to be made up through supplemental heating. So in this case, the heat pump, the area under graph is representative of the heating load. The white area would be represented all the work that the heat pump can provide. And the orange area is representative of the added supplemental heat that would be needed to make sure that home is maintained at temperature. And further along in the presentation, I'll kind of talk about different types of supplemental heat between gas and electric. So I just want to pause there. These are kind of important factors to understand and see if there's any questions. Online or in the room. All good?
Yeah.
And
all good online.
Is this all like everyone knows what I'm talking about? This is no new information, or is this some people's first time seeing this kind of assessment? Sorry, I didn't get a response there, but okay, I'll continue. How do I get rid of?
It's a good starting point, no problem.
Okay. How do I get rid of? Oh, here we go. No. Get rid of the lines drawn. Are they going to stay on my screen this whole time?
You need to find the eraser on the pencil and erase
Right.
You should
Clear
be
all
able to
drawing.
clear all, yeah.
There we go. There we go. Okay. So let's talk cold climate heat pumps. So first, what is a climate zone? Because I'm going to refer to that. A climate zone is basically how we divide up regions of the province based on how cold they are. So you can see Vancouver, Victoria is our climate zone 4, pretty mild winters, couple cold snaps each year, nothing too bad. As we move out, climate zone 5, Kelowna, Whistler, or I guess Whistler is 6, Kelowna, Kamloops, Penticton, 6, Prince George, Prince Rupert, 7 is Dawson Creek, Fort Nelson, and I'm not even sure if there's anything up in climate zone 8. But it's basically an indicator of sort of relative temperature and kind of changes how we would design for a different climate zone. So what is a cold climate heat pump and what's different than a cold climate than a conventional heat pump? So conventional heat pump is rated at that 8 degrees Celsius. In Canada, has to have a minimum HSPF2 of 4.9, and that's using climate zone weather climate zone 5 weather, and doesn't have a cutoff temperature, but typically these conventional units tend to cut out between -5 and -10 degrees Celsius. So, that's not really reliable for real cold climates. Even in Vancouver, we have many days that are -5 and colder. So we have to, be ready for colder temperatures. So Energy Star came up with a cold climate definition that looks a little bit different. So again, the rating stays the same. It's rated to 8 degrees Celsius, but it's tested at -15 Celsius. So we get that capacity factor. And we understand what kind of performance we should expect at colder temperatures. The HSPF2 goes up from 4.9 up to 7, so like a 40% increase in efficiency for these units, because that's really important that if you're going to be using a heat pump, it has to be more efficient than, say, electric resistive baseboard heating. So they've made a requirement to have these units be more efficient. It has to have a minimum COP, that minimum coefficient of performance, of 1.75 at -15 Celsius, and being able to maintain at a minimum its 70% of its rated capacity. The cutoff temperature for these units, again, aren't specified, but typically between -20 and -30. So a much more robust unit that would be much more reliable in cold conditions. So this is kind of that same graph we saw earlier, but now instead of looking at heating loads and heat pump loads, it compares standard heat pump to a cold climate heat pump. So this is a Mitsubishi unit, and what we can see here is that the Mitsubishi in red is a pretty flat line across a wide range of temperatures, so it can maintain really high capacity. It's not till it gets to that sort of -10, -15 where the capacity starts to drop off. These, I have to say, are rated values, and they give a big range here of that drop off, 76 to 93% drop off in capacity. And that's for things like defrost. As this builds moisture, it can frost up coils, so it needs to have its own internal heating to avoid that. So it could be variable in terms of its actual real world performance, but rated, we can see that this maintains good heating throughout at low temperature versus the standard that just kind of cuts out at that, -8 sort of area. So that's kind of the primary differences between cold climate versus conventional equipment, is really being able to maintain that heat throughout a wide range of temperatures, as well as having a very low cutoff. This definition is constantly changing. Department of Energy in the US put together a next generation challenge, already challenging manufacturers to push above and beyond that cold climate definition. And what they want to see is now, instead of operation at -15, they want operation at -26. They want 100% capacity at -15, versus that 70% that we saw from Energy Star, and COPs going up from 1.75 to 2.1. So an increase in efficiency to actually make the business case for using heat pumps at these type of temperatures, as well as low GWP refrigerant. So low GWP means low global warming potential. That indicates the refrigerant itself, when it's released into the atmosphere, has an impact on global warming, and that's measured and quantified. So there's programs looking to reduce the amount of impact these refrigerants have, and I'll talk about that later. What's the phase out? But already the DO is challenging, so the timeline for that is already like they've got 8 manufacturers. They're in field testing. They've had some good data from their field tests and looking at developing or commercializing a product in the next few years. So I think the target is in the next 4 years-ish that all these kind of next generation cold climate will be readily available and produced at wide scale. So that's kind of the target. So design considerations for heat pumps in general. So for any location and any climate. There's a few key features that make heat pumps different than conventional heating systems. And I'll kind of run through a few of them now. But one of the big areas that people feel that have an impact is on the supply air temperature. So the temperature of the air coming out of your air handler or furnace. When we look at operating temperatures of a heat pump, they're much, much lower than conventional gas or electric resistive systems. So your heat pump, even on the warmer days, is producing probably a supply air temperature anywhere between like 28, 29 degrees and maybe as high as 30, 35 degrees, but maybe depends on the product. So when you're looking at trying to heat a home and maintain it at 22, uh, heating up with 27-degree air, it's going to take a long time. It's also not going to feel as hot to you. If you're sitting by a duct, by a vent, and you're feeling that air, 26, 27 doesn't actually feel like it's warm. So a lot of people are like, oh, my heat pump's broken. It's not feeling hot. It's just, no, we're used to temperatures of 40 plus, or if you're electric baseboard, very warm, radiant heat coming off of a unit. So a lot of complaints stem from, I don't think my heat pump's working. It doesn't feel hot, but that's just the nature of how it does. So it takes a long time to respond to changes in temperatures. And one of the key points is we're used to maybe shutting off our heating when we leave for a period. If you go away, if you go on vacation, maybe overnight, that they caution against how long you'd want to shut off your heating or reduce your room set points because it takes so long to bring it back up to temperature. So if your home is occupied, they say don't use night setback. Leave it at a low and slow, constant temperature throughout, so it doesn't have to respond to changes. But one of the bigger implications from a design standpoint around this low supply air temperature is, especially when we're talking about central system, is ductwork. So the amount of energy to deliver to a space is the temperature of the air times the quantity of air. How much air and how hot it is how much energy is delivered to that space. Well, we just said the temperature is now not as high as it was previously. So that means we need more airflow. But does the existing home's ductwork, is it able to accommodate that higher airflow? So there might be constraints within it. It might not have fan power. It might be sized too small. And it may need modification or replacement to actually be able to work with a heat pump. So this could be costly, a costly upgrade if you have a conventional gas furnace. If you don't have air conditioning, usually if you have air conditioning, oh, it just jumped around. I just got an unstable internet. I just want to make sure everyone's still with me.
Yeah.
Perfect.
Yeah.
Yeah. So, if you have a furnace and it is already equipped with an air conditioner as well, typically for air conditioning, you need more airflow anyways, so the duct would be upsized. But if you're a heating only furnace, then it may be problematic and need some modification. So some ways of managing this, there's some like kind of trickier ways to deal with it, is by modifying the existing ductwork and using a combination of ducted and ductless system. So I'll go back to, let's get my pink drawing. So we have our outdoor unit. We have refrigerant lines now going into the house. So say existing system was, this whole home was ducted. You had a furnace, say it's in the attic, gas fired, and it had ducts going throughout the home to all the rooms. In this example, what you could do is actually cap off the ductwork going to the whole home and add in some ductless systems. So in this case, we have one refrigerant line going to a ductless system in the living room, a ductless system in the bedroom, and then the existing ductwork is now capped and utilized for, just say, in this case, it's a bedroom, an office, and a bathroom. And what this allows for is that we can still use a lot of that ductwork, that existing system, as a central system. We can still reach a lot of spaces, and we don't have to go through the whole home and expand and upsize the ductwork, but we can just supplement spaces that the ductwork can't reach with ductless systems. So this is kind of a neat way to design around some of those constraints with duct limitations. So any questions kind of on that piece?
No questions.
Okay. Another piece, kind of design consideration with heat pumps is the location of the outdoor unit. So that, if we recall, the outdoor unit that contains that compressor, compressor can be quite loud. It can be big and bulky. So noise and aesthetics often come into play, especially depending on the types of homes we're looking at. Certainly, I live in Vancouver. I'm in a townhouse. We're very close to our neighbors. There's not a lot of outdoor space. It comes into question of where could we put one of these noisy, bulky units that it's not going to be a disturbance to someone who doesn't have a heat pump. So that often comes into play. I should say on the noise piece, though, there is a lot of work that's being done by manufacturers to limit the noise, and they've gotten pretty good at insulating these things, so they don't cause too much disruption, as well as vibrations. I don't have it up here, but depending on how it's mounted, vibrations also need to be considered. And then condensate is a big one. So in wintertime, when the heat pump is in heating mode, the outdoor coil actually gets so cold as it's absorbing energy from the outdoor air that condensate forms over top of these coils. So that happens during kind of the more mild temperature range, like the 5 degrees to -5 degrees Celsius, where there's still a lot of moisture in the air. As we get colder, the air actually tends to be a lot drier and we don't get as much condensate. So depending on your climate and location, you might be getting a lot of water in the form of condensate pouring out the outdoor unit. So location is really important because it can really ice up. So this is, you can see in this picture, it's an example of a unit being mounted in the kind of the side of the house at a walkway. But this can be very slippery and become a tripping hazard for people walking around the house. So there needs to be some consideration around that use, location, drain. I've had customers come in who've had issues with their location just because they're pouring it out over their front walkway and they get a buildup of 2 inches of ice, especially in Vancouver where we have this our winters live in that moisture range, and they could get a lot of water here. So something to really consider in terms of that design. And then, like any home renovation project, installation quality plays a huge role in this. However, I think with heat pumps, just because they're so sensitive in terms of that supply air temperature, any shoddy workmanship, it can stand out a lot more than, say, in conventional fuel systems where there's just so much heat that you may not notice a little bit of a draft or a little bit of leak. But when you're dealing with these kind of low supply air temperatures, any sort of cold inrush you can really feel it. So things like building penetration. So we have, again, refrigerant lines going from the outdoors to inside. They need to be properly sealed and insulated so no air comes through and no moisture comes in that could affect the building envelope. Proper insulation of the refrigerant lines. So the refrigerant lines also, they're carrying heat in and out of the unit. It's from outside to inside. So if they're not properly insulated, you're just losing heat through those refrigerant lines before it even reaches your home. So both on an efficiency standpoint, as well as occupant comfort. And then refrigeration leaks, if it's not properly connected and sealed, refrigerant can leak out of the system. and that can cause poor performance of the system, as well as there's, you know, the environmental impact of refrigerants leaking into the atmosphere. So these are examples of poor envelope penetration and refrigerant lines just not insulated, resulting in some poor performance. So covered a lot so far, and just want to pause again for any questions or discussion at this time.
Do you hear me?
Yep.
Yeah, so moisture touched on that. I understand, like more so on the coast, moisture with heat pumps is more of an issue. Prince George, do you have any insight as to how effective heat pumps are with the moisture levels we have here?
Yeah, I mean, the heat pumps themselves handle moisture very well. It's more just a consideration of that condensate. Like, in terms of dehumidifying, that's like, you know, like we have air conditioners that can be set to dehumidify and make sure that air is maintained comfortable within your home and you don't grow mold or have any issues like that. So that I think they're pretty effective at. Having said that, though, I was recently talking to a colleague who had a heat pump install, and he said, you know, heat pump was working fine for 15 years, and then when they went to replace it, because it was kind of end of life, 15 years, newer technology, they pulled it out and actually found that there was a lot of moisture on the refrigerant line set in the wall of his home. So in that situation, it was a case of just poor insulation. They were getting cold refrigerant lines, moisture was condensing on it and causing some mold issues. So it kind of goes to that point around install. But in terms of location specific, there's plenty of examples of it working in Vancouver, which is a very moist environment. So I haven't looked at the climate in Prince George, but I know it's a lot drier, shouldn't have any problems. That condensate piece, just in terms of locating the outdoor unit, that is something that everyone will experience, just because you do have a good bulk of hours around that freezing mark in winter, and that's when that condensation is going to form. So it just needs to be managed. It's not challenging by any means. It just needs to be, you either have to drain it or not locate it in a place you're going to be walking or what have you.
Harry, Steve, I have a question. On Facebook, often it comes up advertising for Arctic heat pumps. Are they the ones you're talking about that would be suitable for our climates here in Prince George?
Sorry, say that one more time. Just what type of heat pump?
They're advertised as heat pumps.
Okay, I found this on the web for say that one more time.
Sorry, I'm just the audio's it's loud enough. It's just cutting in and out a little bit.
They're coming. They're advertised as Arctic heat pumps.
Arctic, yeah.
Are they the ones that that the DOE is maybe trying to push for over the next 4 years to suit our climates and further north?
Yeah, I'd have to look at that specific product. I feel like that could be just a branding, because a lot of, you know, I use the Energy Star cold climate rating because it's such a big organization recognized. I've heard the DOE units referred to as Arctic, but there's also other organizations that also have their own criteria. So like there's the Northeast Energy Efficiency Partnerships have their own definition of what a cold climate heat pump should be. So different regions might specify different other factors. But yeah, I've heard reference to Arctic. I'm not sure if it's that spec specifically, or if it's just a different brand. But it's really easy to see. You can always just do a product search, and all the product needs to be tested and rated now at different operating temperatures. So right now, that -15 Celsius temperature, all product in cold climate has to be tested to it. So you just pull up the spec sheet and say, okay, my furnace is 60,000 BTUs. How many BTUs am I getting at minus 15? And then, maybe it's, in this case, in some case, maybe it's 40,000. Then okay, I need 20,000 BTUs of supplemental. Okay, great. I will continue on. So what about design considerations specifically for northern climates? So this is probably what you guys want to hear. So when we're looking at, and I'm going to touch on both electric supplemental and gas supplemental, which is also called dual fuel. So how do we size a heat pump? How do we select one? Do we want it to cover all of our heating? Maybe we just want it to be sized that it could take us to 0 degrees and then switch over to another system to take us the rest of the way. So supplemental heating in Vancouver and the Lower Mainland in our climate zone 4 is not actually needed, but anytime we get into colder regions of the province, we're going to need some supplemental heating. Even in climate zone 5 that spends most of its time at minus 10, they're still going to have days at minus 15. They're still going to have some days probably at minus 18, minus 19. You need something that's going to make sure you can get through those coldest parts of the year. So how do we size with respect to a supplemental system, and what do we consider? So there's ways, we consider energy costs, we consider types of supplemental systems, the capital costs of the whole system, and the emissions may be associated, as well as the resilience in extreme cold. So those are kind of what I think about when I say, okay, how would I select a system, and what do I think is good? So what is a heat pump with electric resistive? So going back to our first conventional system, we've got our outdoor unit, we've got our refrigerant lines, we've got our furnace or air handler system with our refrigerant coil. So an electric supplemental is an electric resistive heater that is located downstream of the heat pump. So what this means is that because it is after the heat pump can do all that it can do, all the heating, and then the electric supplemental can kick in and top it up. So it means that these two systems can run simultaneously. So it can be sized as like the whole heating load. So going back to that 60,000 BTUs, or the supplemental could be sized only for the 20,000 BTUs and the heat pump size for the 40. So this is kind of the benefits of electric supplemental, is that it doesn't need to be the whole 60,000 BTUs. It can work with that heat pump together. This helps to reduce your operating costs. It makes the system overall more efficient. But electric resistive is less efficient and more costly than a heat pump. So how big of a heat pump, how big of an electric supplemental system should be used? When we're talking about dual fuel, it's a little bit different. So in the dual fuel setup, so this is our furnace again, you've got your fan, you've got your gas burner, and you've got your heat pump. And why is it set up like this? It's because that's how it's always been built. Historically, it was that you had a gas furnace, and then on top of it, you would slap in air conditioner. And now that we've replaced an air conditioner with a heat pump, they still have that same configuration. But the problem with this is that the gas is going to heat way hotter than the heat pump can actually heat. So as soon as air comes in, it goes across our gas burner. It's coming off at 40 degrees Celsius. It's already above the operating temperature of the heat pump. So the heat pump can't actually run. So, advantages in terms of a gas system is that, it avoids us adding additional electrical loads, or, gas is cheaper than electric resistive. But when we do get into colder temperatures, the heat pump just becomes completely obsolete, and you have to fully switch over to gas. So you can only run one source at a time, which is now, adding to more greenhouse gas emissions, and maybe it can cause some issues just on the controls and commissioning of the system to make sure you're actually getting the full benefit of a heat pump. So what that looks like for costs, just to compare cost of heating. So not utility cost, but cost of heating. So this includes the efficiency associated with, say, a gas system versus an electric heat pump. So blue is our heat pump. So our costs range, from what's this, close to $10 a gigajoule. But as it gets colder and the heat pump loses its capacity, the cost goes up. So it can actually range as high as, $22 per gigajoule of heating. Compare that to gas, which is flat because a furnace and gas-fired systems are going to be operating at the same efficiency and kind of consistency throughout, which is like your $15.50 per gigajoule. So we can see the -5 is kind of that temperature where the efficiency of the heat pump starts to drop off, that it actually becomes more expensive to operate compared to gas.
Is that -5 Celsius or Fahrenheit?
Celsius. Yeah, good point. I gotta label my graphs better.
Okay, and I think there's a question from back a little bit if it doesn't offset you.
Yeah, let's do it.
Paul asks, you didn't say anything about ground source heat pumps. Are they too small a part of the market to bother with? Are they significantly more expensive than air source?
Yeah, that's a great question. And I focused everything on air source, but the same concepts can be applied. So the same, challenges with capacities, supply air temperatures, these design conditions. But yes, on ground source now, you have a much more stable source temperature. So the air temperature that we're using might be -5 one day, it might be -30. The ground is very stable. It's going to be a very similar temperature throughout the entire winter. The reason why we don't see a lot of them, at least in the province, because primarily these, when we're talking about Lower Mainland, air source can provide a lot of heating. Ground source is just expensive. You have to dig up your backyard. You're going to have to lay a bunch of lines in the backyard, probably down 6 feet or more below frost line. And it just becomes a costly measure. The actual heat pump, the only difference, if we go back to let's go, I jump to slide 1 here.
You froze for about 10 seconds there.
Oh no. So what was I saying? Yeah, so the main difference when we're looking at ground source is really just what the outdoor coil is using to capture heat. And so the biggest thing with ground source and why we don't see as much is just cost. If you can do it with air source, it's just a fan and a heat exchanger outside. When you're doing it with ground source now, you're digging up your backyard, you're laying lines all throughout. It can be a very costly upgrade, but the advantage is, if I jump a couple slides ahead, when we're, looking at heating loads, the output, the ground doesn't get to -25. Oh, why isn't it? Sorry. The ground doesn't get to -25. The ground is going to stay sort of in this range of temperature. So the output of a ground source is going to stay high. So all's to say, ground source is very effective. It's more stable. It gives you high output. It's just the cost for installation, because you need to get a lot of ground area for heat exchange. That's where the problem happens, or that's why they're not as widely used. Does that answer the question in a long-winded version?
Yeah.
So yeah, going back to our costs, I guess, if we're looking at ground source, for example, we would probably cut our graph here. So a ground source would always be lower operating costs compared to a gas-fired system. and it would always maintain higher efficiency because it's not using that source temperature that gets any colder. Any follow-up questions to that?
No, we got a thanks from the person who asked it. Very good.
Okay, so let's talk annual operating costs for electric supplemental systems. So the green on the graph represents the cost for the heat pump, the blue, the cost for an electric supplemental system, and then these outdoor temperatures in Celsius are different switchovers. So depending on how you size your system, the annual operating costs are going to be different depending on your reliance for supplemental. At 2 degrees, we can see here we have over $2,000 in in cost to heat the home every year. Well, the heat pump is going to cost $700 a year in operation. Well, $1,500 or so is in electric resistive heating. As we can see, as you size your heat pump for larger and larger, so it can operate and meet your home's needs at colder and colder temperatures, not only does your operating cost go down because the heat pump is more efficient than electric supplemental, so the total cost goes down, but we can see the portion that the heat pump's contributing. So it takes on more heating load. So we can see at -5, we're probably at like 1,600. At -15, we're, 1,450 or so in terms of operating costs. So we can actually reduce the annual cost by, what looks like $600, $700 by using a heat pump all the way to its limit of -15 before engaging with supplemental. Comparing that to gas, first thing we notice in using gas as a supplemental system, there's no scenario where it is costs over $2,000. So it is cheaper to operate a dual fuel system. And this is climate zone 6. So this would be Prince George and similar. What's kind of interesting is that if you size your heat pump too small, so say, in this case, I did it for +2, but it actually costs more on an annual basis than 0, because the efficiency of the heat pump is better than gas. It makes sense to, until that -5, it makes sense to actually size your heat pump a little bit larger to capture a lot of that heating season at 0 degrees towards -5. As we start getting colder and colder, we saw on the previous slide in terms of costs, the heat pump starts to lose efficiency. The cost for operating the heat pump goes up. You become more reliant on a higher cost system, so that the costs tend to accelerate. Again, it's not a big range. Like if the graph kind of shows it, but this is looking at a total. I think the total between whether you size a heat pump at 0 degrees or -15, the increased cost at -15 is like 6-7% more than at 0 degrees. So it's not a big range in terms of added operating costs for using a heat pump over a gas backup system. Same slide, I just want to show how that breakdown looks now. We've got the heat pump in blue and the gas system in green. At 2 degrees, the heat pump's contributing, very little. You're largely on gas. At -15 on the other end, the heat pump's doing a lot, and you're just sort of topping up that little bit with gas systems. So comparing the two systems, whether you're doing electric, a heat pump with electric supplemental, a heat pump with a gas backup, or also called a dual fuel, you could see kind of how they compare. This was my best case at modeling. There's different inputs, but sort of gives a sense of what it might look like. I am realizing there's some notes in the chat here, so maybe I'll see. I'll monitor the chat going forward. So it was just the question on ground source. Great. So yeah, any questions? Like, let's have a little discussion around, I know I've presented a little bit on sort of cost between heat pumps, whether you're using a gas backup, whether you're using electric backup, any sort of thoughts, feelings from the room or online, based on what you've seen here.
I'm not sure if your data is helping me, but I've been struggling with this myself. Do I put in a mini split ductless heat pump or a dual dual source duct system? And then if I'm doing that, do I do the supplemental heat as heat coils or natural gas, and what the cost differentials are? I think that's part of what you were trying to cover off there, but it wasn't clear to me.
Yeah, I mean, it's case by case because there's a lot of factors to consider. It's looking at climate data, like if we look at like different operating points, so say we pick -5 as our kind of design temperature. If you go with the supplemental system, we're looking at like, call it $1,600 a year. If we're going with a gas system, it's going to be closer to 1,300. So it's roughly $300 in savings to use a dual fuel system versus dual fuel versus electric supplemental. So if you're simply saying costs alone, that's all I care about is I want low cost, then yeah, that might push you towards a gas backup system. Again, there's so many other considerations just because, what's your available electrical capacity, what's your ductwork like, what's your configuration, that I can't give an answer. It's going to be case by case, but just on fuel costs alone, it makes the case for dual fuel. But, what I jump to is a slide I haven't shown yet is around like maybe GHG savings are very important. And, with gas supplemental system, so if that's your driver for installing a heat pump, at -5, you're doing a great job eliminating around 70% of your emissions. But do you want to go that full 100% and be essentially zero emission using electric supplemental? Not quite zero, but 99% emission reduction. So does that additional $300 in this example justify the added greenhouse gas emission savings? And then in terms of sizing, I'd say the typical approach or that I would see in areas outside Lower Mainland is a lot of people size their heat pump for cooling, because that's kind of the driver. They say, I previously didn't have cooling. I want cooling. I might as well put in a heat pump because then I get that benefit of both emission reduction, lower cost heating, and the cooling. And then those switchover temperatures tend to be closer to the zero mark. So it's a bit of an undersized heat pump. You're not getting as much emissions reduction, and then you're still kind of reliant on your supplemental system. How does these changing costs, capital costs, play in with the emission reduction? Well, I tried as best I could to get all the data I had to map out what it would cost. So I put in different size systems at different operating points. And so here we see on y-axis, it's emission reduction. On x-axis, it's costs. And kind of one of the interesting trends to see here is that you get a fairly linear cost as you're getting to that -5, that 70% reduction in emissions. So but then as you start to get really big, going into that -10, -15 heat pump, the cost, you can see there's like the slope changes. It's pretty steep. So we're starting here, say 13,000, maybe as high as 22,000. In that range for our first 70%, but then to get from 70% to 85%, so just another 15% emission reduction, You're going now like 22 grand up to like 27 grand. Like it becomes more expensive to install those larger capacities, and you get diminishing returns as far as emission reduction. And the reason being, there's just not a ton of hours at those cold temperatures. So you're upsizing this whole system to -10, -15, but you're only seeing it run at its full capacity for 100, 200, 300 hours a year. So maybe a week, maybe 2 weeks. And the rest of the time, it's operating at sort of more reasonable -5 condition. So there is a balance point. I think -5, I think province-wide is a really good balance point in terms of where to size heat pumps, just because we do have so much heating at that temperature and above, and then below we start to see that drop off. So and it becomes you're just not utilizing all this capacity you paid for as you get into colder and colder upsizing. So some key points around this. So all electric systems, so electric supplemental will have the most greenhouse gas emission reduction. Properly sized heat pumps with electric supplemental can improve the cost effectiveness as long as we're minimizing the use of electric resistance. It also helps avoid things like panel upgrades and additional electrical capacity you may not have. Gas supplemental has the lower costs, but these costs may increase as carbon taxes change over the next few years. Not sure what direction they're going at this point, but that could have a big impact on the cost of gas. Properly sizing a heat pump with gas supplemental needs to be based on your preferred factors, or what's motivating you. Is it strictly cost savings? Are you just looking to add air conditioning to your existing system? Are you motivated by the environment and greenhouse gas emission reductions? All those need to be considered to kind of optimize for what's best for your situation. Larger heat pumps can add a significant cost since there's just few hours at those extreme colds, so it's underutilized capacity. So just another thing to consider in terms of that design. I'll check. Do we have any questions in the chat or in the room?
Anybody questions online?
Nothing online in the chat, at least. Anyone?
We got a couple in the room. You have to come up here, please, and talk into the mic.
Can't hear me from here?
No,
I mean, you could try.
there are people complaining online.
Yeah.
I'll talk like this, so I still have to talk loud so people in the room can hear me.
Okay.
Quieter. You did talk about air sealing and insulation a little bit. What about passive house? Like when, in combination with passive house, when you get to the point that things are air sealed and super insulated, so that then you might not even need, there's not going to be as big of a range in the internal temperature. I know that some people talk about you basically just need a hairdryer to heat the house. That's when it's too passive. But what are the, yes, how do I put the question? What are the recommendations for that? Because I know that's one thing that I hope to do before I even consider a heat pump.
I think you've answered your own question within that, and that's exactly the approach. The first thing we say to do before even whenever you're considering home renovations and upgrades, and the single most cost effective is air sealing, making sure outdoor air is not infiltrating your home. So whatever you can do to bring down heating loads is going to save you in the long run in terms of operating costs and equipment upgrades. So passive house, I would say, is like kind of the far end, a bit more extreme end of things in terms of their design techniques. But certainly looking at windows and building envelope and insulation and air infiltration, those can all help improve your home's performance. And then after that, you look at putting a heating system that's sized for the new loads, which can be very low. So yeah, definitely design techniques. I would say just cautioning that like window replacements can be very expensive and have very long paybacks. So kind of that number one thing that we encourage is reducing any leakage, like just sealing up the home so you don't have air infiltration. Is the number one kind of energy benefit that you can do to your building envelope that isn't too costly and has great results.
There are heat or HRV, some sort of ventilation. Is a heat pump, does that provide ventilation at all, or
No, it
that
doesn't.
combination with?
It's a good question. Yeah, so heat pumps are just the heating component. They would be, the ventilation would come in combination with another component. So whether that is just a HRV that's going to be doing air exchange, or whether the air handler or furnace